building it for the lessons. Could I please ask the one thing, could you please try and stick to 15 minutes talk? I'm very sorry, I know you spent hours preparing, but it would help. So we've got a little bit of time for questions. I'll indicate when there's about 2 minutes to go. Please, wherever you are, just go to your conclusion. And I apologise in advance, but I've been asked to be very strict. So, without further ado, could I please ask Soyab Adal Kareem, and I won't even need to pronounce the first word of your presentation. Okay, I do apologise, sir. Over to you.
Thank you very much for your invitation. My name is Soyab Adal Kareem. I am assistant professor at Gaziantep University, Faculty of Aerospace and Aeronautic Engineering. So I would like to introduce today my presentation about bifurcation plot of rectangular symmetrical-laminated composite material plates. So let us go through this paper. First of all, introduction. I would like to talk about plate external applied force. As you can see, this equation is non-linear. In the classical method, we linearize this equation using approximation. We'll approximate sine theta equal to theta. So if we approximate this, of course, and if you solve it, and if you solve theta and theta dot and plot this one, this is called phase spectra, you will see that orbital like a circle or orbit or elliptic. This is true because we linearized the motion, but actually it's not linear. So the behavior is non-linear. So how can we solve it? Of course, using MATLAB, you can discretize this equation and solve it using Range-Coulter method. And the plot is the phase portrait at different level of excitation. Look here at low level excitation. Instead of circle, here we have, it's not circle. Here, look, we see 2 orbits instead of 1. Here we have many orbits. So the behavior is completely changed. So, of course, we don't like to see a lot of plots. What is the solution in order to condense all these plots in one plot? We use this plot. This plot, in the first range here, the orbit, of course, here we have doing we are cutting here, and plot. For one orbit, we plot 1 dot. For 2 orbit, 2 dot, and so on. So, and here the state variable, of course, here maybe the excitation or the maximum angle. So, as you can see here, in the first range, we got 1 line. In this range, we have 2 lines. So this range, we have a lot. So actually, this is true only when the behavior is linear. So the behavior is periodic. At this range, we have double periodic. Here we have this happening. It's like just this one. Shift F5. Which one? Shift F5. Yeah, okay.
You can use this one as well.
Okay.
As well.
So how can I make next?
Here.
Next. This is the next. This one.
Next, the next. Here, this point.
Here, next. Yes. So of course we are able to linearize sine theta here or cosine theta just only at low level of excitation. If we have higher level, of course we cannot make that linearization. So at low level of excitation, the behavior is linear or periodic. So let us see. Look here. Here the behavior here. It's not working.
I just suggest you just go it up and just talk way through it.
How to start?
So I can teach you.
Yes. I will use here. This is not working.
Yeah.
Okay.
I think by the time we solve that,
Okay.
time will be up. So.
So, just to brief this point. So, the behavior when the excitation is low level, I got one circle, it's mean linear, or you can approximate your model without big problem using linear model. But if the excitation is big, the linear theory is no more accepted. So, as you can see, so that system does not express the system. So, all this plot I can use bifurcation diagram, which clearly define the linear region and nonlinear region. And of course, here is the transition between linear and nonlinear. So this plot absolutely gives you a full picture to understand the dynamic of the system. Of course, now I am studying the plate. plate, of course, continuous system and show dynamic behavior. The question, does it show behavior like this? Let us see. Of course, dynamic model, I should first use the plate model. Of course, the simplified classical plate theory is just simplification. The general case, it is the bending moment here. Here we have external applied force. Here we have the internal membrane force. Of course, here we have area function. So this model expresses more realistically the behavior of plate. This includes, in addition to bending resistance, it also includes any plane membrane force. So this model expresses more realistically the geometrical behavior or nonlinear geometrical behavior of plate. Of course, this is for isotropic material. You can do this the same for you need, of course, change D for composite material. So, of course, this is the boundary condition. I don't like to solve all conditions, just I take only boundary where is the inner plane forces appear, which is simply supported, immovable in the plane plate. So this is my plate. Of course, I discretize it using finite element, and I use IBDL using ANSYS in order to discretize this one and also solve time step by step with external applied force, with excitation, 2 by half sine wave, or just only for excitation, and see the response. So I record the response only at the middle point of the plate. And let us see, of course, I don't want to show a lot of steps. Of course, at the here, I apply, of course, uniform distributed load. I record only displacement at the mid. So, of course, it shows vibrating point. Of course, this one, I now need to plot bifurcation. First of all, phase portrait. Then, from phase portrait, I calculate the bifurcation plot. So, this is the procedure. I don't want to explain everything, but please, if you have a question, I will go back to any box and explain what I have done. So, in brief, just make finite element and use Newton-Raphson iteration method to overcome linearity and the Newmark to make time integration. Of course, in order to analyze the result, I use fast Fourier transformation in order to pick the resonance point. And of course, you know that the resonance point is not like linear. Linear, it has one certain value, but for nonlinear system, this value is changed. So this is the procedure. I don't want to show everything. Here just the model, the result model. I compare it with the LISA. LISA is very scientist in vibration of plate. So he plots the dashed line. This is frequency. Of course, linear frequency to nonlinear frequency. Linear frequency is one value for plate. Nonlinear, for every load case, we have frequency. So when you change load, we have different value of frequency. So I compared, I found, of course, he used approximate analytical method. For simple case, I used my method. I found very, very approximate close results. Of course, I want to, this one, I extend this result. Of course, all application stop at this point, showing the behavior using this graph. So now I am doing this for composite material. Of course, this is the result I got from ANSYS, and this one I use MATLAB in order to smooth the function. Okay, so I finished. This is the bifurcation plot for plate. So the first range here is linear behavior, and this range is here. This range from here to it is double periodic, and here's the kinetic behavior. And conclusion, of course, it's clear that bifurcation plot clearly shows the boundary where is linear theory is accepted and where is the nonlinear. Of course, nonlinearity sometimes means some sort of instability. Thank you. If you have a question, please, I will be very happy to answer.
Cool. Do we have any questions, please, on the floor? It's quite interesting. Quite a lot of material there. Sorry to have to be rushed. Anybody, any questions, please? Nothing. Clearly satisfied everyone. Thank you very much, sir. And I think we'll be a photograph, but if I'm nice to see, congratulations.